Everybody, it looks like you're all there, most of you are there. So I was informed that I didn't realize it the other day, but I recorded my last lecture, I guess, in this mode where like you're all there on the screen and I'm just like a small window. Obviously that was not done on purpose. It's a shame, and I'm sorry about that, because I guess the Blackbird looks tiny and like you have to suffer to follow what I'm doing. If I do, I mean, I'm assuming that when you're following live, you can probably still click on my window in Zoom. So at least I hope that those of you who were able to follow live could follow easily. But in any case, if you have problems, let me know, because I can see my black whiteboard and hear myself well, obviously, but it's hard for me to tell if you are okay out there. So anyway, today I am being more careful and I'm recording the way I should. I hope. I'm learning along the way, you know, to use these tools. I would like, rather than taking questions right away about last lecture, I would like to start out with some more thorough review of some of the math that we have been and will be using. So the idea is that I am going to, I guess that the most important, what I think is the most important thing for us is that we understand a bit better what a differential equation is. So today I will try to go, I'm not, this is not supposed to be a math course. So unfortunately, this cannot be as detailed as mathematical description of differential equations, but it's supposed, hopefully it's useful to understand how these tools, these concepts are applied to physical problems, like the problems that you will be facing in this course. So the book that I'm following today, it's called Advanced Calculus for Application, and the author is Hildebrand, okay? I'll type it in the chat so you have a written document of this. But I'm not suggesting that you should buy this book. I'm just going to follow a small portion, a few pages really of it. But in case you're curious and you want to.
Good morning, sir.
Excuse me?
I just said good morning.
Good morning. Thank you. Yeah. So, like I was saying, it's just a few pages of the book that I'm going to use today, but they are pretty dense pages, and I think it might take our entire lecture. So let's get started on this, and After we've gone together.
Sorry, sir.
Yes.
Sorry, sir. This book is written by author.
I couldn't hear you. Say that again.
This book
Yeah.
is written by author. Who?
I typed everything in the chat.
Oh,
So if you
okay,
look at the chat, can you read the chat? So you see the last entry is the name of the book.
Hildbrand Advanced. Yeah. Advanced Calculus for Application.
It's written in the chat, guys. Open the chat. It's
okay. I saw it.
I don't mind standing like this for a few minutes, but it's not worth it. All right. You can always email me later and ask me, hey, what the hell was that book? And I can even send you a PDF. No, I would never do that. All right. So seriously, who is written? Yeah. So the author is Francis B. Hildebrand. Professor of Mathematics, Massachusetts Institute of Technology.
Okay. Thank you. Thank you.
All right, let's get to work. So, yes, I'm opening my notes here as we speak. Now, I hope, maybe it was a bit of a brutal approach. I hope it didn't turn you off too much, but I decided rather than starting out with the formal definition, you know, a differential equation is blah, 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 I showed you a case in nature where we basically naturally encounter, when we think of waves, immediately the differential equation that we met last time sort of emerges. And that's the case in many situations in physics. So differential equations are a mathematical entity, but I would claim that they exist because physics need them, because we need them as a tool to answer questions in physics. And the physics of waves is a fundamental example of that. But today I will try to do it a mathematical way. And let's start. Well, the formal definition we already gave. It's a relationship. A differential equation is a relationship between one or more functions that are not known, that are unknown, and their derivatives. So, studying a differential equation, usually we try to find these unknown equations. Okay, so a differential equation is a relation between one or more unknown functions and their derivatives. The simplest differential equation that I can think of is the equation that states that the derivative of a function f is equal to some function h. So typically, h will be some sort of known function, and f is an unknown function that we want to determine. Today, if you're faced with a problem like that, you know, I could give you a string of numbers, right? And I could tell you, open MATLAB and solve this using a MATLAB routine. You could do it basically without even thinking, without even knowing what you're doing. That would be a numerical approach to solving these problems, and there's nothing wrong with doing it this way, but it's a bit limited. In this course, we want to understand, to be able, not necessarily to solve any differential equation, that would be very hard, if not impossible, but we want at least to understand what it means to solve a differential equation analytically. It means that we want to find a mathematical formula for this function f that automatically verifies this equality. We will see, we have seen an example of that on Wednesday. We will see more example of that starting maybe today or for certain on Monday. Now here, for now, let's leave it generic like this. We assume that h is some function that we know. We assume that we can have some mathematical formula also for h, right? But we'll get to that later. For now, let's leave it general. In principle, it could be anything. So my first question for you today would be, I mean, like I said, I'm not expecting you to be able to solve any differential equation, but this is a fairly simple one, right? We only have a first order derivative here. There's only one variable involved. H is a function that we know, and that's all. So my question is, what's the solution to this equation? Like, is there a way that you can think based on the calculus, on the math that you've done earlier in your life, that we could propose to write a solution for this equation?
Maybe we can integrate h.
Yeah, yeah.
Integrate h,
so
and
one way to approach the problem, one possible clue, of course, it's not immediately the solution, but if this is true, then by the definition of integral, also we know that the integral of the left-hand side must, let's take it, well, must equal the integral of the right-hand side. I'm applying the same operation to both sides. And I know that, and this is the fundamental theorem of calculus. So if you've done a calculus course, you've seen it before, and maybe you've been given some proof of it. The integral of the derivative of a function coincides with the function itself. Okay, so f is equal to the integral of h of x. This is only part of the story. We have to be a bit more specific, but this is the fundamental idea. We use the fundamental theorem of calculus to basically look, the point is, if we are able to calculate this integral, if once we know h, hopefully we are able to calculate this integral by the rules of integration that we've learned in school, and so we are done. But there's something else that we have to be careful about. Here, I'm not writing any limits of integration.
yeah.
So that this integral without the limits here, in practice, it doesn't really mean anything. So to be more precise, what I need to do is to state that the integral from minus infinity to x of the f, the x prime, the x prime coincides with the integral also from minus infinity to x of H. Okay, I'm putting a prime here because I don't want to confuse myself with all these symbols. If you don't like the prime here, you don't have to use it. You can just decide that you're going to integrate up to some, maybe it's better, to some point in the x-axis that I'm going to call xi. Okay, xi is arbitrary. So either way works for me. Okay, so now what this gives me, it gives me f of xi minus f of minus infinity equals to essentially the primitive function of h. I'm going to denote it like this, calculated at xi minus the same thing calculated at minus infinity. Okay, so this is not really an integral, it's just, it serves to denote the formula for a function whose derivative coincides with h. Okay, so now if I what does this whole thing means in practice? It means that this guy depends on xi, this is constant. This depends on xi, this is constant. So let's bring all the constants together, and what we get is that f of xi equals the primitive of h evaluated at the point xi plus a constant. Okay, and now if now you can forget, if you want, you can forget my whole derivation of this formula and just take the derivative of this guy to convince yourself that we did it right. And if you take the derivative of this equation, you get back the original differential equation. You immediately find the original differential equation. So I decided that I wanted to go through this little exercise, but it's not mandatory. I could have just thrown at you the conclusion that if this is true, this must be true as well, okay? Because here at the left-hand side, you have f. So if you differentiate it, you get df over dx. Here you have the primitive of h. So if you differentiate it, you get h. And then the derivative of the arbitrary constant is 0. But it's very important that you understand that there is this arbitrary constant involved. Okay. Another way to state it, if I insist a little bit on the math, not because I want you to learn all of these views, but because I'm thinking that you probably have seen this before, but you might have seen it in different ways. So another way of stating this is that when I played this trick here to integrate left and right, the choice of minus infinity here was completely arbitrary. I could have solved the same problem by integrating from any point in space along the x-axis. Depending on where I pick this point, this constant changes, but this expression is still a solution of the differential equation. What does it mean, a solution? It means that if you plug the expression that we found for f in here, you immediately verify this equality. Okay, so let's just keep the stuff that's useful and delete the rest. Good. Okay, so now a little bit of vocabulary. A differential equation, like some of you mentioned on Wednesday, has an order. The order of the differential equation is the highest order of differentiation that you see in the equation. If the highest derivative of an unknown function, the highest order derivative is the third derivative, then you have a differential equation of the third order. What else? If the unknown functions that we deal with are function only of one variable, we speak of ordinary differential equation. So this is a differential equation of the first order, and it's ordinary. Okay, you probably heard the acronym ODE before. ODE, it means, we tend to even forget that it means ordinary differential equation. An ordinary differential equation are to be distinguished from partial differential equations, or PD, which involve partial derivatives, or in other words, which involve functions that are functions of more than one variable, and that within the equation are differentiated with respect to more than one of these variables. So on Wednesday, we actually met, we started immediately difficult, right? We immediately met a partial differential equation. But then it was a good one because we were able, playing some tricks, this strategy that's called separation of variables, we were able to transform it into two ordinary differential equations. As a general rule, ordinary differential equations are much easier to solve than partial differential equations. Okay, so if possible, if you have the opportunity to turn a partial differential equation into a combination of ordinary differential equation, you might want to take that opportunity. And then another important property of this differential equation is that it is linear. What does it mean for a differential equation to be linear? It means that it does not contain products of the unknown function with one another, or powers of an unknown function, or nonlinear function of that unknown function. What does it mean, a linear function? Basically, it means that you multiply the function by a factor, okay? So either that factor is a function of the independent variable, but it cannot be a function of the function. Okay, so for example, you know, the derivative with respect to x of the of f equals the cosine of x, that would be nonlinear. Okay, this is a nonlinear function of f. But we are not going to deal with this kind of equation in this course, if I'm not mistaken. So basically, we stick to linear. We won't go beyond second order differential equation, which could be partial, because when you deal with waves, basically, you always deal with space and time. Even if you place yourself in a one-dimensional world, like we did on Wednesday, where you have only one spatial coordinate to describe the phenomenon you're observing, you still need a second independent variable, which is time. So the physical equations that describe wave propagation are usually partial differential equations, but linear and second order. I'm anticipating, but you will see that happening as we go on. So now I gave you the simplest possible differential equation that one can think of, and that one, basically, we have a recipe to solve it. We turn it into an integral. So then the problem is to solve the integral, but for that there are plenty of methods. But that's not usually the case. Like I said on Wednesday, as a general rule, when you are faced with a differential equation, it's not granted that a solution exists, okay? You might be unable to find a solution, and you just have to live with that. That's not the case in the problems that we will face in this course. But anyway, the most general linear OD can be written in one fairly compact formula. Basically, it's a sum of derivatives of f up to an arbitrary order that I denote n, like the typical integer number. So from n, you start adding some lower derivatives. And each multiplied by its own coefficient that I'm going to denote by a also with an index, all the way to the 0th order derivative, which is the function itself. In the most general case, these coefficients are also, by the way, a function of x. So let's allow for that. Okay, so that would be the most general linear OD that one could. I mean, it's not the most. It's the most general description for a linear OD that I can think of. Okay, we only have n minus, well, n rather than n plus 1 independent coefficients, because if there was another coefficient in front of the nth derivative, we could divide everything by it, and we would be back to this form, which is slightly as one less, as I say, degree of freedom. So I would say this is the most general expression for a linear ODE. So now I cannot, I'm sorry if I repeat myself, I've been saying now many times, there's no recipe to solve. I cannot give you a formula, this is the equation and the solution is like blah, blah, blah. I can do it in this very simple case, but not in the most general case. But I can show you some general properties of such an equation that become extremely useful when we look for the solution to an equation that has this form. To do that, I have to introduce or recall a concept in vectorial algebra that becomes useful in this context as well. And it's the concept of linear dependence. So this morning, while I was preparing this lecture, I thought about it and I thought to myself, okay, I try to cut the math a bit short and so that we can move on to the physics, because after all, we don't have so much time to spend together. And I was thinking initially, maybe I'll do vector algebra and like these concepts in math that are kind of abstract for some of us, like Euclidean vector spaces and Euclidean spaces, and like this concept of linear dependence and linear independence in a sort of more detailed way. But then I thought maybe that's not worth it. But then, like the question that is in my mind right now is, do you guys like how, if I say linear dependence, does that strike a bell? Like, forget ODEs for a second, but if I tell you that two vectors are linearly independent or linearly dependent, what does that mean to you? You know, like in 3 dimensions, can you give me an example of two vectors that are linearly independent in the 3-dimensional space, X, Y, Z, you know? It's a question for you guys. And remember, I don't want elegant math answers. I just want some rough I just want to have a feeling whether you can even say we've never heard, we don't know, you can say that you don't know what I'm talking about, you know, that will certainly help me organizing my next lecture. But you know, like you have, if I draw a reference frame in 3D, right, and I tell you this vector is directed like the x-axis, okay? It's a unit vector, 1, 0, 0 in the direction of the x-axis, and this vector is directed like the z-axis, okay? It's the unit vector that points up. So are these two vectors linearly dependent or independent from one another?
Independent.
Bravo, very good. So why are they independent? Because I'm not like this is the ugly explanation, right? We get to the nice one in a second, but I cannot obtain one by simply multiplying the other by a scalar. Okay, they are not parallel, in other words. So if you've got only two vectors in 3D and they're not parallel, the mathematicians, in the mathematical language, usually we say they are linearly independent. Okay, if the vector x, unit vector in the x direction 1, 0, 0, and another vector 4, 0, 0, these two vectors are linearly dependent because 4, 0, 0 is equal to 4 times 1, 0, 0. Okay? Good. But now let me get to the more formal definition. Which is that, well, the thing is, okay, I need you, now I hope that you remember what it means for, well, we might as well write it. Like, so if you have, excuse me, I'm sort of thinking, brainstorming while I speak, how can I best explain these things? We say that n vectors are linearly dependent if there exists a set, if there exists, I don't care about the set, if there exists n coefficients let's call them Cn, and the vectors I'm going to call them Un. When I underline, it means that it's a vector, okay? I do it without thinking, so you have to get used to that. Let's call it V. It's probably better than U because my U looks like my N. So a letter, whether lowercase or uppercase, that underlined on my whiteboard, it means a vector. If it's not underlined, it cannot be a vector. If I underline it twice, it's a matrix, but we'll get to that later. So, so n vectors Vn are linearly dependent. This is a definition. If there exists n coefficients Cn such that the sum C1 V1 plus C2 V2 plus blah 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 plus Cn Vn is 0. Or, you have to get used to these things if you aren't yet. The compact way of writing is big sigma with k that goes from 1 to n of ck vk equals 0. Okay, so these are two ways of writing the same thing. When you see this big sigma, some of you, probably most of you, have seen this before. It means that the index k here takes all the values, integer values between the first one here and the last one up there, and the sigma means that we are summing them up. Okay, it's a sum. It's exactly the same thing as what I wrote to the left, but of course here I'm forced to recur to these dots, which is kind of not a very complete description of what's going on, right? Okay, so this is fully unambiguous once you accept the definition of big sigma. Okay, so we agree with the notation. Now, what you have to take home here is that this is a definition for linearly independent vectors in general. Usually, when you think of a vector, the most immediate metaphor for that, the most immediate example for that is a point in space, right? If I want to describe the position of objects in a three-dimensional volume, in a three-dimensional space, I use their coordinates in the x, y, and z direction, which are 2 horizontal and 1 vertical axis. That's what we learn usually to do. And so these vectors would be groups of 3 numbers, each associated with one of these coordinates. Okay, so I'd rather not do a full vector linear algebra, basically because I'm supposed here to do waves, but I can always, if you have specific questions, we can always talk outside of these meetings, and I can try to help you to at least find the right place to do your review. So now, the point here, and I'm sorry if I say too many things, but the point here is that what this equation is saying is that n vector are linearly dependent when you can find a combination, a sum, okay, weighted by some coefficients here, such that one of these vectors can be written as a combination of the others, okay? Can be written as what we call a linear combination of the others. So if this is true, if these vectors are linearly dependent, it means, for example, that, I don't know, V2, any of these vectors, so let's just take V2, can be written as minus, I just bring everything to the right-hand side, so minus C1 over C2 V1, plus, minus C3 over C2 V3, minus blah, 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 all the way to Cn over C2 Vn. Okay, why am I wasting time on this concept if what we want to study are differential equations? Because a big, an important innovation that appeared in applied mathematics after the concept of vectors was invented, mostly to simplify the description of some physical problems, is that the idea in vector algebra were applied to other fields in mathematics, like that of differential equation. And the important point, the important concept that I need you to grasp for this course.
Sorry, sir.
Yes.
I remember definition linear dependency is not exactly like you are right. I think.
Yeah.
I think you forget the condition is exactly unless exists one coefficient Cn different 0. I think definition that you right is not exactly. I think so.
Could you write could you write the right formula on a piece of paper and show it on your screen? So it's probably, I would tell you to come to the whiteboard, but
I think you forget one condition is at least exists one coefficient Cn different 0.
Ah, yes. Yes. Thank you.
Okay.
I'm sorry I didn't understand you exactly the first time around. You're perfectly right. These coefficients have to be different from 0. Yes.
Yeah.
Otherwise, what I've said
At
doesn't
least,
make much sense. Yes.
at least.
If.
Okay, sure.
Yeah. Thank you. So. Yeah. Okay. Yes. Thank you. Yes. 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 Of course, that's an important condition for these things to make sense mathematically. So now, thank you. So now, what happens next is that I want to apply this concept to functions. Okay. So just like we have linearly dependent or independent, if this is not verified, they're called linearly independent vectors, we can think of linearly independent or linearly dependent functions. And the definition is exactly the same. Imagine that you have a set of functions. I'm going to use the letter F to denote them, and again an index K, defined on some portion of space. So X is between some extremes A and B. We always stay in one dimension for now to keep it simple. So we say that these functions are linearly dependent if for all values of X, there exists as n coefficients, again, C, K different from 0, such that the sum, this sum equals to 0. Now, the reason this concept is very useful in geometry is that you can define a base, a base of vectors to describe the space where you work. For example, in geometry, you can define 3 vectors. One, if we are in R3, so if we are in the 3-dimensional space, you can define, I hope you can still, yeah, you should still see the blackboard. You can define 3 vectors which point in a direction of the 3 axes. Okay, 1, 0, 0 points in the x direction, 0, 1, 0 points in the y direction, and 0, 0, 1 points in the vertical, in the z direction. And then you can write any other vector in the 3-dimensional space as a combination of these 3 vectors. That's what you do when you indicate the coordinates of a point in space. Just like latitude and longitude are a perfect, useful tool to identify a place on a geographical map, if I want to define a point in this room, and I want to define it with numbers, I want to know exactly which place I'm talking about, well, I can use the walls of my room, the corners between the walls in my room as axis of reference, and then I can just measure the distance of this point from some origin, like that corner down there, the distance from that origin of any given point in this room. And those three distances are basically the three coefficients I multiply these vectors by to find the vector that points to that particular point. So I'm being a bit fast with these concepts because I'm assuming you've seen them before, but you can always contact me later to ask questions. Now, what is perhaps possibly for some of you a bit more complex is to think that also in a situation, okay, where the possible configuration of some object are described by a set of functions, then it's useful to be able to reduce the set of functions which might be infinite to a discrete base, and then any possible configuration is a combination of the elements of that base. This is a bit abstract, and which is why we soon see some specific examples. But you might already start thinking about the problem that we will study in some depth very soon, the problem of the string. Okay, imagine a guitar string. You've all seen a guitar string before. So it's a string of a fixed length whose extremes, whose endpoints are fixed. And when you hit it, it vibrates, okay? And this string can take an infinity of shapes, right? But we will discover that to describe any possible crazy shape that the string might take, it will be enough to identify a set of functions, of very simple functions. And I might as well anticipate that those will be the cosines and the sines of x. And we will learn that whatever shape the string takes, we can write it as a sum of cosines and sines. This might be a bit abstract still for some of you, but the idea of these lectures is that as we go on, if you bear with me, things will start coming together and eventually they make total sense. Whether or not these examples are helping you, the message that the one thing that you need to take home today is that we reviewed the concept of linear combination in linear algebra and geometry for vectors. And I'm telling you that you will learn that this concept becomes useful also when we are faced with a differential equation. And now I'm going to try to show you how that happens. Okay. You've learned a few minutes ago, and I'm going to use now these new notations that we've introduced. You've learned that the most general form for an ordinary linear differential equation is now let's just keep it the way it's not worth it. So we've learned that it's something like this. Okay, and I promised you that I would try to give you some insight into the meaning and the properties of this mathematical beast. And the first exercise that I propose for us to do is to think of another very simple case, but a bit more difficult than the one we've seen before, of this equation. And that will be the case where all these coefficients, a n minus 1 and a n minus 2, all the way to a0 are all constant and identically 0. Except for the first coefficients here, which is always 1. Okay, so this is nonetheless still nth order linear ordinary differential equation. But it's a bit perhaps easier to somehow manipulate. Okay, so any ideas, like thinking of what we've done with the other differential equation that I showed you earlier, like what could we do here to see if we could make it simpler? Maybe, yeah. Let's think of a specific example. Okay, so we have an unknown function that I call f, and I know that its third derivative with respect to x is equal to twice x to the power of 5. Could be, okay, that one day in nature you find a problem that boils down to an equation such as this. Let's imagine that that's the case. So no abstraction anymore, okay? This is a specific example of a differential equation. So how would you go about trying to solve it? You've done some integral and derivatives, so you know how to take a derivative. You know, in some simple cases, you might know how to take an integral. So maybe you are able to give it to give me some suggestions of how I could do this. I could go about this. Here is a hint. You shouldn't think very far from what we've already done today.
We integrate.
Yes, very good. So if you integrate it once, okay, I integrate this guy once, I discover that the second derivative of f must be equal to the integral. The integral of this guy is, yeah, I don't know why I took the power of 5, but whatever, my bad, right? Plus some constant. I call it whatever, I call it A, capital A, right? If you're not convinced, just take the derivative of this. The derivatives are easy, right? If I take the derivative left and right here I get the third derivative of f. Here I get twice x to the power of 5, and a just goes away because the derivative of a constant is 0. So surprise, surprise, we are back with the equation that we started with. Unless I did something wrong, but I don't think I did. I don't know. If it's wrong, it's not very no. I'm just kidding. I didn't do anything wrong. So now you already solved it, right? You already know what's going to happen next. You integrate it again, and what's going to happen is that, well, the first derivative of x now must be equal to x to the power of 7 multiplied by 2, I think. No. 1/3 x to the power of 7. No.
No.
Yes.
It's 7 divide 21.
I think this. No.
21, sorry. 21.
3 times 7.
Anyway, once you've written, it's easy to verify that it's right? So, yeah. So if I take the derivative of both sides here, I should, and I think I do, recover the previous equation. And then, so from here, we've gotten to here, and then, sorry, the whiteboard is becoming a bit of a mess, but still reasonable, I hope. So finally, f of x equals 1/21 times 49 x, no, still get it wrong.
No.
Well, 1 over some big number, x to the power of 8, plus a, you're going to calculate this as an exercise at home, please.
168.
168.
Type it on the chat. Thank you. No, I mean, I appreciate that you're participating and staying with me. It's just, yeah, integrate 3 times. That's right. Yeah. So I'm under. Yes. Okay. Thank you. Yeah. Let's assume that you got it right. In any case, the important thing is that you understand the trick, right? So, so I have. Here you've got.
Sorry.
I put a question mark here, and I think about it when I am more relaxed. Okay. So what I really care about, guys. Yeah, 21 times 8 equals 168. Sounds good. So, but what I really want you guys to care about are these 3 arbitrary constants. You remember I explained to you that when we solved that really easy differential equation with just the first derivative, we necessarily had to accept that we would have an arbitrary constant in the solution. So we didn't have one solution, but we have an infinity of solution. And whatever the value of that constant, the solution would still be a solution, okay? It would still verify the equality that we started with. So we have to call it a solution. Now here, what happens is that we have a 3rd order differential equation, and we end up, okay, this is a solution because we have f here, okay? We don't have some strange function of f. We don't have a derivative of f. Here we have the function that we have to plug in the original equation. Okay, so this is the solution, and the solution now contains 3 arbitrary constants. Okay, so I could. This is not a rigorous proof. Okay, but it's a simple exercise, relatively simple exercise, to show you an example of what turns out to be always the case. If you have a linear ODE of order n, the general solution, that its solution will contain n arbitrary constants. Or in other words, you have an infinity of solutions which are defined not by 1, not by 2, but by n arbitrary constants. To select one specific solution, you have to select n values for this arbitrary constant. So maybe now, if you think about what I've done a minute ago with vectors and linear dependence, you might start to see a connection here. If you allow me this expression, the word of functions that are solution to this equation, okay, can be described in this way. Basically, it's a linear combination of this function here, x to the power of a, this function here, x halves x squared divided by 2, this function here x, and then this function which is constant, a constant. Okay, so what we've just found is that any linear combination of these 4 functions will be a solution to this equation. Okay, that's one thing that I would like you to think about. Okay, so it also means that just like when we have to describe, if you are an architect and you want to describe how much space the whiteboard and the heater and my table are going to take in this room, you need to know the coordinates of the endpoints of these objects. And for that, you need basically 3 coordinates, which is the same as saying you need 3 vectors, one pointing up, one pointing that way, and one pointing that way, for example. Once you've selected these 3 vectors, 3 numerical values are enough to describe the position of any point in my room. Okay, so that's a linear combination of 3 vectors. Now, when you're dealing with a set of solutions, with a word of what possible solution to this equation, it works sort of in the same way. We found here that we need 3 functions or 4 functions of x to fully describe any possible solution of this guy. Okay, so this is not really a rigorous demonstration. I showed it to you through an example, but I think it's pretty clear that this whole idea applies to this general equation here, and n can be an integer number. So if the order is 3, then I get 3 independent arbitrary constants here. And if the order is n, I'm going to get n of them. Okay, and now, once again, not a rigorous proof, because this is not what I've written here. This is what we've solved here. And I'm going to call it equation 2 star. We've learned to solve equation 2 star. You integrate 3 times, like your colleague nicely summarized it. If the order is 3 here, you integrate n times. If the order is n, we have a recipe to solve this guy. but I'm not giving you a recipe to solve this guy, but I'm asking you to believe me if I say that the main, well, one of the main points here still applies to equation star. And that point is that order n means n arbitrary constants, or for n plus 1 linearly, if we count also the constant, which we should, as a linearly independent function, n plus 1 linearly independent functions to describe any possible solution to this problem. Okay, so I didn't phrase this last point very well. What I'm trying to say is that if I was a good mathematician, which I'm not, I would have given you a rigorous proof that this guy, the general solution to this guy is the combination of n plus 1 linearly independent functions. Because I'm not, I decided to show you a simple case, a simpler case, where we can actually find a recipe for the solution. In that particular case, I've shown you, and I hope I convinced you, that the fact that we have order n here implies that we end up with n arbitrary coefficients here. And I'm asking you to make a little bit of a logical jump and to say, okay, I understand, I have a feeling for what's going on, and I believe that the same idea will apply also to a more general ordinary differential equation where we have a lot of derivatives other than the derivatives of order n. Okay, that's copied from the Hildebrand book, and for me, when I first studied ODEs, it was convincing enough. But do you have any questions? You have more time to think about this, because what we are going to do in the next few lectures is apply these ideas to some practical problems. But before we move on now to apply these ideas to waves, which we will do very soon, there's another important point that I want to make about what it means to solve a differential equation. So what I try to convince you of at this point is that finding what we call the general solution of equation star here is the same. It means finding a solution. One way to phrase it, it's not the best, but it's intuitive to me, a solution that contains an arbitrary constant. It's not very rigorous. A better way to phrase it would be is to find a solution, is to find an expression that verifies that equality and is the linear combination of n plus 1 independent, linearly independent solutions. And of course, once again, I gave you a recipe for solving the easy case where all these coefficients a and -1 and -2, a and -2, all the way to a1, a0 are all zeros. But then, if you want to find finding a general solution of star doesn't mean really anything in practice, because depending on how these coefficients are like, and they can also be function of x, and how this h of x is like, then finding an actual solution will be a different story each time. Okay, so, but there are some tricks that we can always try to play. And one of them is to break the problem into two problems. One is finding the solution of the associated homogeneous equation. What does it mean, homogeneous? It means that the term here that doesn't contain f, what here I denoted h of x, is 0, okay? So the homogeneous equation associated to star, I call it star h, is equal to 0. To simplify my life, I'm going to define what we call an operator L. Basically, I will introduce a symbol L, which we apply to F, and which means the combination of all these operations all applied to F. Okay, and then this equation star h becomes simply LF equals 0. Now imagine, you don't know yet how, but imagine that you can find two solutions to this problem. I'm going to call them F1. So you find some function F1 of x that verifies that homogeneous equation. And another one I'm going to call F2. So if they both solve equation star, well, by definition, it means that this operator L applied to F1 gives me 0, and the same when I apply to F2. So, but then this also means that if I sum LF1 plus LF2, I get 0. And because this is a linear operation, if I apply L to the sum of F1 plus F2, I also get 0. So more generally, I might state that if I have n independent, well, if I have n solutions to star h, so which I call fk with k that goes from 1 to n, then any linear combination of these equation is a solution to my homogeneous equation. Okay, so if you have n solutions that are independent from one another, they're not just multiples, so to say, of one another, you have a general solution to this guy. It doesn't necessarily simplify things in practice, but at least you know that once you have this base of solutions to a homogeneous equation, you are done. You have a solution. And we will see this will turn out to be useful. Now, I want to go back to equation star. And which I can also write as L F equals H of X. Well, now what we notice, if we think about what we've just done for a minute, is that if I find just one function, and I'm going to call it f and h, that satisfies equation star, well, then if I sum f and h multiplied by a constant c prime, no, without constant c prime, f and h plus the sum of all possible homogeneous solution, fk, I have now a general solution also to star. So the bottom line is that what in most cases we do in practice when we are faced with differential equation, non-homogeneous differential equation, is we separate it into we extract from it the homogeneous equation. We solve, if we are able to do it, the homogeneous equation, which in any case is simpler than a non-homogeneous one. And then just being able to find one specific solution that solves the non-homogeneous is enough to get a general solution to the whole, problem. So important here to realize that f and h is one particular solution of this problem, while this is the general solution. So I have 4 minutes to take your questions, after which I will encourage you to think about this a bit, because it was probably, if I was in your place, I would think this was a bit of a difficult lecture. But starting on Monday, we will again go back to some specific problems in nature that involve the propagation of waves. But please, if you want, use these few minutes to ask whatever you wish about this.
Hello, sir. Please, with the F and H formula, the general solution formula, you said K is equal to 0. I don't understand why K should be equal to 0, because you said K is equal to 1, 2, and N. The
Yeah.
general solution.
So, okay, so let's go back to this. Yeah, so here, by the way, I should start from 1.
Okay.
I don't know if that was.
That's the question I was asking.
Does that answer your question? Yeah, thank you.
Yes.
It was just after 1 hour and a half, it's almost impossible to get these things right for me. But yeah, just a typo. Anything else? I'm sure you can find something else that is not probably perfect on this whiteboard. Should we call it a day or a morning and convene again on Monday? Oh, and by the way, actually, yes, important. We're not talking about Monday, we're talking about Tuesday. You should have been informed. I have some conflict on Monday, so we had to reschedule my lecture. It will be on Tuesday, same place, same time, but on Tuesday. And then we should be able to continue as usual. Okay?
So, sir, you mean that
Yes.
we don't have a course on Monday? On next
Not
Monday?
with me.
Not with you. Ah, okay, thank you.
Yeah, I don't know. I actually don't remember the rest of your schedule, but you see me on Tuesday at 11.
Okay.
So you're probably free on Monday at 11.
Okay.
All right.
Thank you, sir.
Thank you. Have a good weekend. Email me. You can use